Hello everyone, welcome back. So today I will be solving a problem called word ladder. So it is a very important problem for in terms of interviews, and it is a very popular interview question in Amazon also. So let's go through the problem statement once. So let me zoom it a little bit. So here it says given two words, one is begin word and one is end word, and a dictionary of words which is a list of words. We have to find the length of shortest transformation of sequence from begin word to end word such that only one letter can be changed at a time, and each transformation of word must exist in the word list. So what this basically means, so before that, let me go through these notes also. It says that return 0 if there is no such transformation of sequence, all words have the same length, only words contain lowercase alphabets of characters, and you may assume that no duplicate words in the list, and you may also assume begin word and end word are non-empty. Okay, so let me just go through this example over here. We have begin word as hit, and we have to reach this word cog. So first of all, before reaching, we have to check if this cog is present in this dictionary or word list or not. If it's not present, the answer is 0. Cog is present, so it is possible to reach to cog. So what is the possible way to reach? Remember, only one character can be changed. So this is the possible path. So from hit we go to hot. Hot is in the dictionary. From hot we go to dot. Dot is in the dictionary. From dot we go to dog. From dog to cog. From dog to cog. So four edges are present. So the length is 5. So we have to find out this. And now for this example, we see cog is not present in the word list. So the answer is 0. So this problem might not seem like a graph problem, but this is basically a graph problem where we have to somehow make this thing as a graph and find out what is the shortest path to reach from this node to this node, where each of these letters or characters are as a node of a graph. So we have to construct a graph. So let's go to the whiteboard and see how we can construct a graph using this. Now I have written down the example from LeetCode where the begin word is hit, the end word is cock, and the word list or the dictionary is this thing, the list of words. So now, as I have told, this is a graph problem. So somehow we have to find a way to represent these words as a node of a graph, and we have to find the minimum path to reach cog from hit. So how we can just think of this as a node of a graph? So before doing that, you must remember that what is the single operation which is allowed. We can only change one character of these words at a time, and all of these words will be of same length. So now, first of all, let me write down the initial node of the graph, so which is hit. So this is the initial node. So after that, from here we can change any one character of this of this node. So for doing that, what we will be doing is we will be first checking all the combinations of these three letter words, where first, let's say, we put like this hit, H I T. So here we first will put A, then B, then C dot 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 Z. So we will be having words like AIT, BIT, CIT dot 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 ZIT. And now among these many words, we will be checking if any of these words are present in our dictionary or not. So if any of this word is present in our dictionary, that means there must be a H between this hit and that word which is present in our dictionary. But here we can see none of these words is present in our dictionary. So now what will be our next operation? Our next search will be putting from A to Z in this second location. So the words will be HAT, HBT, HCT dot 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 Z HZT. So these many words. So now I will be checking if any of these words present in this, any among these words are present in this dictionary. Here we can see there is somewhere in the middle we will be finding a word hot, because here it is we are changing I to O. So this hot is present over here. So we have to make this a node. So now it will be hot, and there will be a edge between them. so hot. So after that the same process will be done for hot. So now our next word is hot. So I will be again checking if any node is present after hot. So hot, again we hear a to z, we check aot, bot, zot. If any of these words present here, we have to check. Yes, there is one word present here, and what is that? That is dot. So we have to connect hot to dot. So now we connect hot to dot. Now after that, for the process will be same. Now you are getting, I guess. So from dot, where we can go? From dot we can go to dog. So from dot we can go to dog. So from dog, where can we go? From dog we can go to either lot, sorry, uh, from dog we can go to log. Log, okay. And from log, where we can go? We can go to cog. So here we can see we have reached our ultimate destination, and what is that? That is cog. So what is the path we take? So how many edges are there? 1 2 3 4 5. So we will be taking total 5 steps for reaching from hit to cog. So what are the steps? Hit to hot, hot to dot, dot to dog, dog to. So here one thing to notice is that we can see from dog we can actually go to cog also and log also. So here we don't need to do this like a separate level. Here we can see from dog, in that iteration itself, from dog to log also, whenever we are changing this position, we first go to cog and we then go to log, so they will be of same level. So now if we calculate, we having 1 2 3 4. So this is the minimum way to reach from hit to cog. There if we do like this and here we write cog, we are unnecessarily putting one extra level. So that is not required because this cog is already reachable from dock. So that's why we will be putting it here. So that part we have to also take into consideration. So after forming this graph, there is a simple BFS traversal will do us our job. And why we are doing BFS? Because we have to find out the shortest path between two nodes, and for finding out the shortest path we use BFS. And for BFS we will be using a visited array, or we can say visited hash map. So this visited hash map will be uh, taking count of or taking track of whichever nodes are visited. So first of all the nodes in this word list will be uh, all the nodes whichever are there in the word list will be false. So like hit, first of all, there will be there, it will be false. Then hot will be false, and so on. So all of them will be false. So first of all, a simple BFS will be like we will be using a queue, and we will be inserting this hit into the queue and making it from false to true. So after true, we will be checking what all are the adjacent of hit. So we will be finding hot. So now we will be appending that hot to the queue and making it true. And we will be also keeping track of one counter which will be counting these node values, the edge counter. So how many edges are there? So after calculating all the edges, we will be finding out there are 4 edges, but our answer will be +1 because we have to count how many steps. So 4 edges, so 4 plus 1, 5 steps. So our answer will be 5. So this is our algorithm. So after writing the code, you can clearly understand how we are implementing this BFS. But the main tricky part was here to getting this like forming this graph. So that part is clear, I hope so. And now we have to calculate what is the time complexity and space complexity of this algorithm. So the time complexity of BFS is big O of m cross n. But here this n, which is len of each word, len of each word. So which words I am talking about? I am talking about this, like hit 3, cock 3, all of them are same length. So this n is length of each word, and this m is length of len of dictionary, len of dictionary. So that means this length. So here we can see, for finding out the next node,
we are doing two loops and we are putting all the values, like from a to z we put here, from a to z we put here, from a to z we put here. So that is an n square operation. So the overall time complexity will be order of m into n and into another n, because we are doing extra n work over here to find out the next node. So basically it means m into n square. It is the time complexity, and also space complexity will be the same as this, order of big O of m into n square. So this is our algorithm. Now let's go to the code editor and let's see how we can implement this solution.
So now the code of this problem is little bit longer. So I have already written down the code and I will be explaining each line and what is each line doing. So first of all, we will be checking if the end word is present in the dictionary or word list or not. If it's not present, that means there cannot be a path from begin word to end word, because the ending point itself is not present. So that's why we will be simply returning 0, or else we will be initializing a variable called path length, and we will be taking a queue for BFS and a visited hash map. So as I have said that we will be putting all the words in the hash map, and we will be making them as false. So here we can see for let's say this example, we are putting all the words in the hash map and we are making them as true as false. After that, we also put begin word in the hash map and make it as true, and also we put the begin word, which is the root of, or like the beginning node from where we are starting BFS, in the queue. And after that, this BFS logic is pretty similar. Like for each BFS problem, we do the same thing. We calculate the size of the queue, which actually says that how many characters or how many nodes are at the present level of the graph, and after that, for each node in the present level, we continuously pop them and we see all its adjacents, and we push them into the queue and we make them visited. So now the main trick which is for this problem is how to find out all the adjacents. So for this part we have to write down this code. So what this code is doing, here we can see it's a nested loop where this one is running from 0 to length of each word, which for this example is 3. So for each character we are putting from 0 to 26, and its character like from A to Z. So for 0 it is A, for 1 it is B, for 25 it is Z. So we are putting each character over here and checking. So whatever the new word is created, we are checking if that word is present in our dictionary or not. So if it's present, then we are making that word as a node and we are making that as true, and we are appending that to the queue. So after whole thing, we are incrementing this, the path length, and whenever a node is there which is indeed equal to the end word, we are just returning path length plus 1, and unless and until nothing is found, we return 0 over here. So let's run it. Here we can see accepted, and if I submit it, okay, and here we can also see it's accepted. So that is how we have to solve this problem called word ladder. So thank you for watching. I hope you understood the concept of this problem, and if you did, please make sure to like and subscribe to my channel.